Okay, so we can actually start now, unless you know that there is somebody who really wants to attend this lecture, but cannot arrive in time. Maybe there are such people. Okay, so last time I started talking about Fedosov's quantization, and I formulated Fedosov's. Hello. I ended with formulating Fedosov's theorem, the main theorem of Fedosov's quantization. So let me recall you a few notions. So M is symplectic manifold, omega symplectic form. Then we consider the fiber bundle of Weyl algebras over M with respect to this symplectic form. We make it complex. We introduce a formal variable h bar, and we complete it with respect to the gradient introduced specially for this purpose. The generic section A of this bundle is equal to locally, in local coordinates. In local coordinates. And it looks like A of xy equal to the sum for all p greater or equal to n, where n is some integer, h bar to the power p. That is to say, we allow certain finite negative powers of h bar. That's convenient for some things. And then we add, let's say, take the sum over all multi-indices I, I1, I to n, A, P, I of x, y, 1, I1, y to n, I to n. We further consider differential forms on M with coefficients in this fiber bundle. So a generic element here looks like B of x, which looks precisely like this one, but there will be one more summation sign. So we sum over p over the multi-index I over the multi-index j. We have h bar to the power p, a, p, I, j. Then we have y to the power I, which is the abbreviation of this expression. And also we have dx to the power j in local coordinates. The space of sections of this fiber bundle is endowed with a natural algebra structure with respect to the pointwise multiplication. So we know this algebra by just W hat sub H of M. Maybe there was also C. This C actually means that we allow complex coordinates, complex coefficients here. Nothing else. The purpose of introducing these differential forms was to consider, I'll probably abbreviate the space of Q forms by W hat Q H bar of M, right? So again, the purpose of introducing differential forms was that we would be able to consider connections on a fiber bundle W hat as a map nabla from the space of sections to the space of differential one forms, and further extended it in the usual way to the map of differential from differential one forms, differential two forms, and so on. So this is the space of differential zero forms, right? And so now we have a whole complex of differential forms on M equipped with the differential induced by a connection. Of course, when I say differential, it would mean that D is a flat connection and D squared is equal to 0. If you are familiar with the theory of vector bundles, you would probably argue that it is not always possible to introduce flat connections on an arbitrary vector bundle. And that's, of course, the case here as well. However, in the situation that we are now, this obstruction, the topological obstruction, can be somehow circumvented by the virtue of the fact, by the virtue of this fiber bundle being infinite dimensional. So this, since this is infinite dimensional, we can actually make it flat. And I explain how this should be done. So let me recall you a few steps of this construction. And then I'll prove the theorem, which I promised. So the idea, first the idea. Since we want, first of all, we would like that D verify the Leibniz rule. The Leibniz rule with respect to the product of sections of W. And that already would mean that we have a very limited set of connections in our disposal. That is to say, if a connection preserves the Leibniz rule, it preserves somehow the algebraic structure of our vector bundle, right? And this algebraic structure is actually induced from symplectic form. So if we try to differentiate something with the help of a vector, of a connection, this connection should kill the symplectic form, otherwise we would have problem with the algebraic structure. And so we need to look for the connection D in the form nabla plus some correction term. This nabla, I mean, you all know that all connections more or less are the same. They all begin with D plus some gauge potential, right? So this gauge potential can actually depend on the structure of our vector bundle. But this D is unique for all of them, right? So this will also contain some D plus gauge potential plus the correction term. Now, if we take this correction term, as we usually will do, in the form of commutator of the elements with certain correction section zeta in a space of 1 forms on M, right? Then this first term will always come from some, geometric connection. The connection which does not know anything about the original structure. So we conclude that this first term should preserve omega, and by preserving it, I mean that it should verify the condition nabla of omega equals 0. Otherwise, we would have problem with the algebraic structure. So again, all connections have this form. If we take the correction term in this way, like this, which is good because, of course, commutators, they verify Leibniz rule with respect to anything, right? So we conclude that this first part would also verify the Leibniz rule. But this part is geometric. So we conclude that this geometric part of our connection should, in fact, look like some symplectic connection. So when this condition holds, and also we assume that nabla is symmetric, then we call nabla symplectic. So the first thing I probably need to prove today is the existence of symplectic connections. After this, we proceed by looking for the correction term which would make our connection D flat. Or in this case, Fedosov prefers to use a different term. He calls this connection abelian, not flat. So we look for zeta such that D is abelian. I'll probably better use the capital A here. So, in order to make sure that this is possible, I argued as follows last time. We can write down nabla, whatever the connection nabla is, we can write down nabla as the sum of D and these Christoffel symbols, gamma I, J, K. Now I can use omega to lower the upper index of gamma by, say, something like this. Right? And since I assumed that gamma was symplectic, I mean, not gamma, of course, nabla was symplectic. And it would mean that this gamma ijk is some, as far as I can remember, anti-symmetric with respect to the last two indices. I thought it was either symmetric or anti-symmetric. Let me see. I don't remember. Sorry for this. And in any case, we can now form the element gamma of y, a local section of W1 hat h bar of m by the formula. So as I can remember, it's something like square root of minus 1 divided by 2h bar gamma I j k y j y k dxi. So it's differential one form, locally defined, of course, because these coefficients are locally defined. But then nabla will look like nabla of A equal to dA plus the commutator of gamma of y with L locally. And this would mean that, so now by direct computation, it's easy to show that the square of this connection the curvature operator of this connection, nabla square, will look like the commutator of A with certain element. I think I used the formula f of y last time, where f of y up to the coefficients, which I totally forget, looks like R I J K L. So R I J K L is the curvature tensor of nabla, and I use omega to lower the index I of this tensor. Now I take this tensor, I take, I think it was, I think it was yi yj dxk dxl. So it's again a locally defined differential form with coefficients in the Weyl algebra. In fact, even though the original tensor was only locally defined, it is easy to see that when you go from one coordinate chart to another, the corresponding formulas will match. So you can actually get a global differential form. So it doesn't matter whether it's local or global. And we conclude that the only chance for us to have 0 here would mean to make sure that this f of y belongs to the center of the algebra of differential forms with coefficients in Weyl algebra on M. That's the only chance. Now, the center of Weyl algebra bundle is easy to understand because Weyl algebras have a very small center at every phi, but it's just a space of scalars. So globally, the center of this Weyl algebra bundle would look like just a space of differential forms. In this case, it will be two forms, right? Right. On M. And we need to take into consideration H bar. So it looks something like this. So I allow negative coefficients, but positive coefficients are indefinite. I allow some finitely many negative coefficients, but only finitely many. And the number of positive coefficients can be infinite. So in any case, it's the center. And if we take phi, an element in the center, and we would like to see, and would like to have that d square of A would be equal to the commutator of phi and A, and that's 0, of course. It would be easy to see from Bianchi identity which says that if you take the covariant derivative of the curvature form, curvature operator, you obtain 0, right? We see that in this case, it will just mean that d phi, which is of course equal to the covariant derivative of phi, because phi is central, so all the correction terms, all the gauge potential terms, they vanish identically. So just d phi should be equal to 0. And we conclude that the condition that should be verified is this. That's necessary condition. And Fedosov's theorem is actually a claim that this necessary condition is sufficient. So let me finally write down Fedosov's theorem. And then I'll try to prove this theorem. At least sketch the proof of this theorem, as I usually do. So, theorem. For every last time I formulated it in a little bit, sloppy way. So let me write it down more accurately today. So let us consider not arbitrary phi, but phi which will begin with something very special. Because if you look at the space of differential forms on symplectic manifolds, differential two forms on symplectic manifolds, which verify this condition, you will see that there exists one special element which is always there. And that's symplectic form itself. Of course, t omega is equal to 0. Right? Always. And Fedosov says that you can always find phi. You can always find the abelian connection, which would start you always find abelian connection if you take phi beginning with omega. So let me write it down. For any phi in a space of differential two forms in M, now with just positive or non-negative coefficients from in H bar, such that d phi is equal to 0, there exists an abelian connection D such that D square of A will be equal to, well, I think it should be minus 1 divided by H bar omega plus phi commutated with A. And that's 0, of course. So in other words, if I take not arbitrary phi, but phi beginning with this term, and all the other terms will have positive degrees, or no negative degrees in H bar, I'll always be able to solve this equation. And that's Fedosov. Main Fedosov theorem for you. So I'm going to sketch the proof of Fedosov theorem now, but I begin with proving the existence of symplectic connections. Let me call the definition. Let omega be a symplectic manifold then there always exists a connection nabla. And the fine connection, I mean connection on the tangent bundle of M, such that first nabla is symmetric. Well, in terms of the Christoffel symbol, we just mean that gamma ijk equals to gamma jik. And second, nabla of omega equals to 0. Vanishes. Let me do this in a old-fashioned way, that is to say in indices. Theorem, okay, claim. On any M omega, so this connection is called symplectic. Nabla is called symplectic. Okay, the claim, the claim is already here, so I'll probably put claim as a part of this definition. So this definition slash claim. And now I'm going to prove this. Proof. Okay. So we will look for this nabla in the following form. We take nabla 0 and add a correction term to this nabla 0. Well, nabla 0 is d plus gamma ijk. So what I'm going, and of course it should be symmetric, right? And there always exist symmetric connections on any manifold, not necessarily symplectic, but symmetric, of course. You just take, for instance, you just introduce arbitrary Riemannian structure in a manifold, and you take the Levi-Civita connection, which is, of course, symmetric by definition. You choose any symmetric connection on manifold and consider the correction terms. So what I do is I take this gamma, delta gamma in the form delta gamma I, sorry, ijk, and then I will use omega to lower the upper index, right, as usual. I denote the correction term with lower upper index by delta gamma ijk. So now this term, this expression, this locally defined set of elements, delta gamma ijk, is in fact symmetric. I mean, or I say skew symmetric, and that's because the original gamma ijk was symmetric, and omega is anti-symmetric. So when I symmetrize, so since, oh, damn it. Yeah. You can always assume, that delta gamma ijk, when you symmetrize it, vanishes. Okay. So let me do this. Now what I'm going to do, I'm going to choose delta gamma in such a way that the condition 2 will be verified. Okay. First of all, I'll rewrite this condition, nabla omega is equal to 0, and as a condition on this nabla, sorry, on this gamma. First I have nabla 0k of omega ij, right? And then I have delta gamma I jk plus delta gamma j ik. And that should be equal to 0. I mean, if you substitute omega here, right, the first term that emerges will be like this. And then if you apply this term to omega, then what you get will be precisely this element. So we need to find delta gamma so that this condition is verified. Okay, so that's how I'm going to, that's what I'm going to look for. So I continue by rewriting the condition a bit further. First I add the 0 term equal to the symmetrization of delta gamma. As I assume that symmetrization of delta gamma should be equal to 0. And this allows me to add this 0 term without changing the result. then, so here I have delta gamma ijk, subtract 1/3 delta gamma ijk, I get 2/3 of delta gamma ijk, right? So this is 0, by the way, again. So nothing has changed, but then I have 2/3 of delta gamma ijk minus these and minus these. And I write it in the form 1/3 of delta gamma ijk, minus delta gamma jki plus 1/3 of delta gamma ijk minus delta gamma kij. Okay? It's kind of a trick, right? But what we also know it is that we want to have this, right? So we can now, if we have this condition, then we can continue this expression. And get one more line. One-third nabla k omega ij plus 1/3 nabla nabla j omega ik. So that's just this condition which is plugged in here. So if I want to have 0, it would mean that I have this equation. And it turns out that this equation is in fact sufficient. The left-hand side of this equation, as you see, does not depend on delta gamma at all. It's something we already have. We just put delta gamma ijk equal to this expression. And then I check that this equation will hold. And what I do is just this. I write it down in this form. And then I check this expression. Jik. So I substitute these terms instead of these expressions. And what I get is 1/3 nabla k. Probably better to say put nabla 0, right? Sorry, nabla 0, of course. Sorry for this. Nabla 0. Okay. Omega ij plus nabla 0j omega ik minus nabla 0 k omega ji minus nabla 0 I omega jk. Right? And I use the skew symmetricity of omega. And I end up with the following expression. It's 1/3 using the skew symmetricity, it looks like this. I think it is, just a moment. Yeah, 3 times nabla 0k omega ij plus nabla 0j omega ik plus nabla 0I omega kj plus nabla 0k omega ji. That this term is a symmetrization of nabla of omega, which is equal, as you know, symmetrization of this expression is just equal to the differential of omega, which is 0 because omega is symplectic. So what we have is just nabla 0 k omega ij, and that's precisely this formula. So if we put delta gamma ijk like this, we always get this equation in the end. Now, before I proceed, let me observe that in fact, this is not a unique way to choose gamma ijk. In fact, if I I think, yeah, if I add any symmetric, totally symmetric in three variables, tensor to this expression, then it will vanish here. And I got again the same expression. So this choice of delta gamma ijk is not unique, unfortunately. And that makes the theory of symplectic connections much more non-trivial than the theory of Riemannian connections. A structure, the description of all possible symplectic connections, is a very interesting part of symplectic geometry. So that was the proof that symplectic connections exist. Okay, so now I'm going to prove Fedosov's theorem. So what do? I'm going to choose arbitrary symplectic connection nabla as my initial term. Since it's symplectic, I can extend it to a connection on the space of Weyl algebras. And this symplectic connection will verify the Leibniz rule with respect to the product of elements in the Weyl algebra. But of course, its square will not vanish. So I'm looking for a correction term. And if I denote, so denote this by dA, then the choice of correction term will be such that d square applied to A should be equal to the commutator of square root of minus 1 divided by h bar omega, comma, plus phi, comma, IA, and that's 0. So now, the brilliant idea due to Fedosov was to use a very special form to choose this correction term, which is of course always equal to the commutator of A with something, in a very special form. This correction term in the form a commutator of A with not just some section zeta, but the first term of this zeta we will prescribe to be equal to omega of y where omega of y is a variant of, you remember we had this gamma of y. So we can use now omega in differential form, omega in very much the same way to obtain this first term here. Namely, I put omega of y equal up to the coefficient which I always miss, I think it's square root of minus 1 divided by h bar, omega ij times yi dxj. Let me check it. My lecture notes. Okay. Just a moment. This omega of y, yeah, that's precisely the form up to the sign. I think it's, yeah, it is, I don't know, even the sign is correct. Even the sign is correct, yeah. Nice. So, what is the purpose of introducing this first term into the play? And the purpose is to get something well behaved as a part of the curvature. First of all, it is easy to see that this omega of y is a well-defined section in this algebra. So it's differential, globally defined differential one form on M with coefficients in Weyl algebra. Let me now denote by delta of A the operator given by the commutator with omega y. A can be any section of this graded space of differential forms with coefficients in M. Of course, this should be graded commutator, right? Graded commutator. And I claim that delta square of A is equal to 0. But that's easy, because delta square will be equal to omega y comma omega y comma A. And by using the Jacobi identity, you can rewrite it in the form of, I think, 1/2 in front of the commutator of omega y with omega y with A. But the commutator of omega y with omega y is easy to compute. It is equal to minus 1 over h bar squared, right? It's minus 1 over h bar squared. Commutator of omega ij yi dxj omega pq yp dxq, right? Now dxq, omega, and omega, they commute with everything. And all that remains, oh, damn it. All that remains is the commutator of yi with yp. So this commutator will be equal to square root of minus 1 divided by h bar. Oh, sorry. Multiplied by h bar, sorry. Pi iq, q or p, sorry, ip omega ij omega pq, and also dxi dxq, right? It's already enough to see that this commutator will be equal to 0 because we don't have y's here. Y's disappear. So this is in the center. This term is in the center, in fact. But it is even more that we can say, because when we sum up over p, we get, since pi is inverse to omega, we get delta iq here. Not I. Is it I? Sorry, that's dxj. dxj, yeah, dxj. Delta iq. So what it is equal to is minus square root of minus 1 added by h bar times omega delta I. So this is replaced with delta IQ, and we can replace Q with I. Omega PI, not the delta IQ, that's incorrect. Sorry. I'm in a hurry, that's bad. It's not good to be in a hurry, right? What we have is, okay, let's take this, right? It's up to the sign, it is equal to plus, right? So it's up to the sign, minus delta pj, sorry, that's correct now, delta pj. What I have here is now plus ip dx p, right? Sorry. So when I multiply like this, okay, it's incorrect. Delta j. Instead of p, I put j, right? jq, sorry. Fine. jq minus delta p j. This p contracts with this p, right? And I substitute j instead of p, and q is intact. Okay, finally. Minus delta pj, that's omega jq, and I have the dxj, dxq finally. That's just omega, right? Square root of minus 1 divided by h bar, omega. Okay? Nice. So it's up to the sign. I was a little bit sloppy with the sign, but it doesn't matter much. In any case, we see that this squares to 0, as I promised.
Before you erase this part, here we proved that delta square root of a is equal to 0, but here, what was the correction term? Because we
some zeta.
This
some zeta. We don't know what. We don't, but we want to take the first term in this correction term in this form. And that's actually very important, because it is this choice which allows us to solve the equation. Okay? Okay, nice. So finally, I have the following form of this D. So choose dA equal to nabla of A plus delta of A, because this commutator with this omega y, we denoted it by delta of A. plus the commutator with this correction term zeta. We want to find we want to find such zeta that d square of A will be equal to the commutator with omega square root of minus 1 divided by h bar omega plus phi. That's what we want to have, right? But if we take it, we see that this will be equal to the commutator of A with the following set of elements. So first of all, I have Fy, which appears from this term, right? Then I have, when I commute this and this, I get nabla of omega. Let me see, nabla of omega y, commuting with A. After this, if I commute this and this, I'll get up to the sign again, nabla of zeta commuting with A. Then I start commuting this with itself. As I explained, it will be equal to the commutator of square root of minus 1 divided by h bar times omega with A. So this is what we want, and this is what we get. We see the first term already appears just from this, right? Then we apply delta to zeta, and that will give us delta zeta commuting with A. Again, up to the sign. And finally, we'll have 1/2 zeta zeta commuting with A. And this last term appears just in the same way this term appeared in our previous talk because of the Jacobi identity. Because if you put zeta here and zeta here, you can rewrite it in this way just because the Jacobi identity is verified by this commutator. Comparing these terms, we see that the equation amounts to the following very simple form. So, sorry. Since I always have problems with remembering coefficients, yeah. I put, so first of all, I think I made a mistake with the sign. It should be minus here with your permission. Okay? It should be minus here. But it doesn't matter. So when I put delta zeta on the left, I get something like this. Delta zeta should be equal to Fy plus nabla omega y, right? Minus phi plus nabla zeta and plus 1/2 of zeta commuted with zeta. It is just this equation where I dropped the commutator sign. They said that, of course, it is not always true that if the commutators are equal, then the elements under the commutators should be equal. But it is enough to have the equality on the elements in the commutator. Sorry, I think it should be something like this here to make it totally correct. To have this equation. And I put delta zeta on the left and all the rest on the right. So you see the first three terms do not depend on zeta. So I will denote them just by omega 0. Oh, probably even, yeah, let it be omega 0. So what I have, omega 0, is this equation. Delta zeta is equal to omega 0 plus nabla zeta plus 1/2 zeta zeta. It is our purpose to solve this equation in terms of zeta. To this end, I need to construct one more operator. So this, it turns out, the fact that it is possible to solve this equation is due to the fact that the operator delta is invertible, or almost invertible. It can be inverted almost everywhere. And to do this, I just show the inverse operator. Those of you who are familiar with the ring functions, you will probably recognize this construction pretty soon. But for those of you who are not, let me just write down the formulas. So I have the operator delta of A. And since delta of A is up to the sign just equal to the commutator of A with some omega, it verifies the Leibniz rule. And hence it is sufficient to define it on elements on the generators. For instance, if you take delta of of something in the center, delta of xi or delta of dxj, you get just 0 because it commutes with everything, right? X and dx, they commute with everything. Now it is sufficient to define, to check what is delta of y, what the delta of y I is equal to. So we just commute. So this delta is equal to, well, up to this pathetic square root of -1 divided by h bar, just to omega pq yp dxq yi, right? Again, dx commutes with everything, omega pq commutes with everything, so it is only necessary to commute y with y. So again, up to the sign, it is equal to square root of -1 divided by h bar omega pq dxq. But here we have h bar times square root of -1 times square root of -1 pi pi, right? I think plus is correct, but I'm not sure about this. Doesn't matter much, because in any case, again, these two tensors, they are inverse to each other, these two coefficients. And what we get, it will be equal to delta, up to the sign delta qi, and hence, it's again up to the sign, it will be equal to plus or minus dxi. It turns out that it's always possible to choose the signs correctly, so it will be just plus. But I don't remember the correct terms, coefficients. So this is actually a definition. We can now rewrite delta as the operator d over dy somehow, informally. dyi dxi. It's a kind of the RAM differential, but with non-commutative variables. Now the inverse, or the conjugate operator, will be denoted by delta star. And it will consist of differentiating over dxi and multiplying by yi. This should be done very carefully, of course, because multiplication by yi is not commutative, right? But you can do this carefully. You can introduce the operator delta star in the correct way, so that delta star squares to 0 equals square to 0. That's not hard to do. And also you'll have the following equation, which is very familiar to anybody who has ever worked with Hodge theory. So it looks like the plus operator, right? Totally like the Laplace-Beltrami operator. So if you apply this to A, you'll get A. Now I need to, yeah, the sign is always the problem. Where is it? Sorry. Where is this sign? Just to make sure. It is equal to, yeah, it is not equal to 0. It is equal to the following thing. It's not equal to A. It's equal to A multiplied by the P plus Q. So here A is an element, a homogeneous element in the space of Q forms on M with coefficients in M, sorry, in Weyl algebra. This Q now is the degree of A as a differential form. And this P is a degree of M with respect to Y. Y degree of A. Of course, this Y degree varies. If you change the order of Y, you have to use this commutation relation, right? To H bar square root of -1 times pi ij, right? But as you remember, this H bar was formerly given the gradient equal to 2. So this gradient is preserved eventually. And this P is precisely this gradient. So if A is homogeneous, then we have this equation. Nice. This is already enough to get the inverse operator. Namely, we put delta minus first of A homogeneous equal to 1 over P plus Q delta star of A if P plus Q is not equal to 0. And 0 otherwise. Then we have the following equation. Delta minus first delta plus delta delta minus first of A will be equal to A minus A00. 0. That's the part of A by grading 0, 0. See? And that's actually the key to Fedosov's construction. So we need to solve this equation. Let me resume from this place. I made one more assumption, which I'm free to do because I have freedom in the choice of zeta. So we can assume that delta minus first of zeta is equal to 0. and also that zeta 0, 0 is equal to 0. Right? In this case, if I substitute zeta instead of a here, I'll see that delta minus first delta of zeta will be equal to zeta.
Sorry, why the minus a0, 0?
Sorry?
Why the minus a0, 0? Why not just a?
Because I have this. This is equal to delta star of a only when p plus q is not equal to 0.
Ah,
Because otherwise we'll have to divide by 0. And that's impossible, as you know. So I need to put delta minus first of a equal to 0 if p plus q is equal to 0. So let me assume that delta minus first of zeta is equal to 0. And this also holds. Then this equation is true. And I can rewrite equation star as zeta equal to delta minus first of omega 0 plus nabla zeta plus 1/2 zeta zeta. Now the operator delta minus first is linear, so I can again rewrite it a little bit further. And get zeta should be equal to zeta 0. So zeta 0 is just delta minus first of omega 0. Just this. Plus delta minus first of nabla zeta plus 1/2 zeta zeta. This is the ultimate form of this equation, and now it's time to solve it. And I'll do this by induction. We put zeta 0 equal to delta minus first of omega 0. And of course, delta minus first of zeta 0 will be equal to 0 because delta square is equal to 0, right? And also, zeta 0, 0, zeta 0, 0, 0 is equal to 0, right? So the condition I put is verified for delta for delta 0 just because omega had these properties, right? And delta minus first only increases the by degree. Okay, nice. And then I put zeta 1 equal to zeta 0 plus delta zeta 0, delta minus first of zeta 0 plus 1/2 zeta 0, zeta 0, and so on, right? Delta 2 zeta 2 will be equal to zeta 0 plus delta minus first zeta 1, I'm sorry, nabla zeta 1 plus 1/2 of the commutator zeta 1, and so on. At the nth step, I have delta zeta n plus first equal to zeta 0 plus delta minus first nabla zeta n plus 1/2 zeta n, zeta n. Let me prove that this sequence converges in the sense of this of the completion of Weyl algebra, which I considered. So the sequence of zeta n converges. What do? We subtract zeta n from zeta n plus 1, and I subtract the right-hand sides of these equations. Zeta 0 will vanish, and what I have will look like delta minus first of nabla zeta n plus zeta n minus zeta n minus 1, right? Plus, and here it is interesting that we can actually substitute the difference of zeta n minus zeta n minus 1 zeta n minus 1 by, so this is equal to 1/2 of zeta n plus zeta n minus 1 commuted with zeta n minus zeta n minus 1. It's just like the famous formula for the a plus b times a minus b, right? It's just like this. It's just this. Now, the y grading, the q grading, the y grading, so the grading in terms of the Weyl algebra. The grading of these elements in terms of Weyl algebra is equal to the grading of zeta n and zeta n minus 1, right? And the same is true about these two. So the term in the parentheses, to which we apply delta minus 1, it has grading, as an element in Weyl algebra, it has some grading which is greater or equal to the gradient of zeta n, right? The term in parentheses has gradient, Weyl algebra gradient greater or equal to the gradient of zeta n. But delta minus first increases this gradient. So we see that this term, the gradient of this term in terms of Weyl algebra, gradient of zeta n plus 1 minus zeta n as element of the Weyl algebra is strictly greater than the gradient of zeta n minus zeta n minus 1. Strictly greater. Right? So the gradient of these elements gradient grows, and hence this difference, well, we can say that it tends to 0, because that's the way we completed our Weyl algebra. That the elements with larger and larger gradient are smaller and smaller, so to say. So we see that this tends to 0. In Weyl algebra. That is to say, more and more terms of zeta n plus 1 remain unchanged as elements in the Weyl algebra. And hence we conclude that there exists a limit of zeta n as n tends to 0, n tends to infinity. We call this limit zeta. It is now easy to see that zeta verifies the equation zeta equal to zeta 0 plus delta minus first nabla zeta plus 1/2 zeta zeta. And it is, it takes a few more steps to prove that if zeta verifies this equation, you see, this equation is the consequence of the original equation we obtained from Fedosov condition. So we need to revert the reasoning that we used to derive this equation to conclude that zeta verifies the original Fedosov condition. It takes some time, but it is not very hard. So the connection d of A equal to nabla of A plus delta of A plus commutator of zeta with A is abelian. I think it's a good time to make a stop here, to make a break.